Hi everyone. Today we'll be presenting our project on reproducing the paper de-identification of free text medical records using pre-trained bidirectional transformers. The problem we're tackling is de-identification of clinical notes. That means removing personally identifiable information, or PHI, from free text medical records. This is crucial because while clinical data is extremely valuable for research, it cannot be shared unless all PHI is removed to protect patient privacy under regulations like HIPAA. Traditional methods for de-identification often use rules or basic machine learning, but they struggle with generalization. So the question is, can we use modern language models like BERT to solve this problem more accurately? Specifically, okay, the original paper approaches this problem by fine-tuning BERT, a transformer-based language model on PHI annotated clinical text. Specifically, it uses BERT followed by a CRF, aka conditional random field layer. And BERT captures context at the token level, and the CRF helps ensure that the predicted labels follow valid BIO sequences. For example, not starting an entity with an I tag. They frame the task as a sequence labeling problem. Classify each token in the text and evaluate using standard metrics like precision, recall, and the F1 score. Our goal was to reproduce key results from the paper using a synthetic clinical dataset formatted like the 2014 I2B2 de-identification challenge. We replicated their pre-processing steps, tokenizing the text using BERT's word piece tokenizer and aligning tokens with PHI tags in bio format. For the model, we implemented both the BERT plus CRF model as well as a BERT only baseline. We trained both using Hugging Face transformers and logged metrics across 3 epochs. We evaluated using precision, recall, F1, and accuracy. So this flowchart illustrates our pre-processing pipeline, where we start with raw clinical text, tokenize it using BERT's word piece tokenizer, and then assign bio tags to each token to identify protected health information.
Here are our results. The BERT and CRF layer achieved an F1 score of 0.825 with precision 0.84 and recall 0.81. The BERT-only model scored slightly lower with an F1 score of 0.79, precision 0.81, and recall 0.77. We also visualized training and validation loss and observed steady convergence over the 3 training epochs. The original paper reported an F1 score closer to 0.89 to 0.92, so our results are slightly lower. There are a few reasons for this. Number one, we trained for only 3 epochs, and longer training could improve performance. Number two, we used a synthetic data set rather than the original clinical notes. And third reason being we didn't do hyperparameter tuning while the original paper likely did. Despite this, the trend was consistent, and adding the CRF layer improves performance, just as the original paper showed. We conducted an ablation study by removing the CRF layer to assess its impact on model performance. We found that without CRF, the model's predictions were less accurate, particularly for longer or multi-token PHI entities. The F1 dropped from 0.825 to 0.79, which confirmed the CRF's role in structured sequence decoding. The BERT-only model often made incomplete predictions, like tagging the first name but missing the last name. The CRF helped correct those by modeling tag dependencies. For biotagging, the B name marks the first token of a PHI entity of type name, for example, Doctor or John. I name marks the subsequent tokens inside the name entity, for example, Smith and John Smith. O indicates outside any entity. So in the example picture, we see that the CRF layer helps ensure that the model learns valid tag sequences. The B name should be followed by I name, not B name followed by O, which is why it performs better in structured prediction tasks like de-identification. This graph depicts the model performance comparison for the BERT and CRF layer and BERT without CRF. The BERT and CRF model had higher precision, recall, F1 score, and accuracy. To summarize, we reproduced the core method from the paper, which was BERT and CRF for PHI detection. Our results matched the trends in the paper, though our absolute scores were slightly lower. The CRF layer made a measurable difference, as shown in our ablation study, and we identified clear areas like longer training and hyperparameter tuning where results could be improved. And that concludes our presentation. Thank you.